Hi guys, we are continuing talking about electrochemistry, and we're actually going to start talking about cells. So remember, we have electrochemical cells and we have electrolytic cells in this chapter, and they're kind of the opposite. So today we're going to start with electrochemical cells, which another name for that is batteries. And these are reactions that are spontaneous, meaning their delta G's are negative, their K's are higher than 1, meaning that they are product favored and spontaneous. So they will occur on their own. And these reactions are spontaneous, and they also involve the transfer of electrons. And so because of that, they generate electricity. Electricity is the flow of electrons. And so keep that in mind, that it's a spontaneous reaction that generates electricity. So a battery, again, is a reaction that involves redox, involves an oxidation and a reduction reaction, and it's a spontaneous chemical reaction. And to build a battery, you need 4 things. So here are the things that you need. First, you need 2 pieces of metal that differ in reduction potential, and those pieces of metal are called electrodes. And so you need 2 different pieces of metal. Let's talk about this reduction potential. So you have some tables here, reduction potential tables. Looks like this. And these are for aqueous solutions, so reactions that happen in water. So you have those. And then you have this table right here that just has single elements. So we are going to look at this reduction potential table here. So reduction potential, which is capital E, this is the reduction potential. And the little degree sign, remember, that means that it's at standard conditions. So that means 1 atm of pressure, 1 molar solutions, and 25 Celsius. It's measured in volts. So, you know, like in your battery, when you see a battery that's like 9-volt battery, that's the voltage, that's the difference in potential. And what it is, it's the likelihood of these to be reduced. Potential means likelihood. So reduction potential means likelihood for these substances to be reduced. If you look at this table, you'll see that these are all reduction equations. Whether you're looking at this table or the table that's in the previous pages, you will see that all of them, you're adding electrons on the reactant side, which means they're gaining electrons. So these are all reduction reactions. And so this is the likelihood for this, for F2 to be reduced to get to F minus, for example. And so you'll see that the high numbers are at the top of the table here. The lower numbers are at the bottom of the table. So I want to make this smaller so we can see it a little bit better. So you can see the whole table here. So the ones that are at top that have the highest reduction potentials, highest reduction potentials, means that these are most likely to be reduced. These are the lowest reduction potentials on the bottom here. And so these are the least likely to be reduced, meaning they're the least likely to gain electrons. And so that means that they are the most likely to be oxidized. So depending on which 2 metals you put together and the reduction potentials, the one that has the higher reduction potential is going to be the one that's going to be reduced. The one that has the lower reduction potential is going to be oxidized. So going back to our battery that we're going to build here, we are going to make a battery out of zinc and copper electrodes. And so those are the 2 metals we're going to use, zinc and copper. So let's look at zinc and copper on this table here. So let's see if we can find them. copper, there's a bunch of them. We're going to use copper 2, and we're going to reduce it to solid copper. So we're going to look at this one right here. Then let's find zinc. Right here is zinc. And so out of these two, copper has a higher reduction potential, so it's going to be reduced. Zinc has a lower reduction potential, so it's going to be oxidized. So copper is reduced, zinc is oxidized. So let's go back to our battery that we're going to build. We're going to take 2 beakers or 2 containers of some sort, and we're going to put the 2 pieces of metal, one in here and the other one in here. Now, which one's which? So we said between copper and zinc, copper is going to be reduced, zinc is going to be oxidized. Well, we call those 2 pieces of metal electrodes. One of them is called the anode, the other one is called the cathode. It is best practice that we draw the anode first on the left side, then the cathode. We go alphabetical. Most of your textbooks and most of the questions on the AP exam will draw them that way as well. The anode will be on the left and the cathode will be on the right, but always double check just to make sure. You can draw them switched, but it's just best practice to draw them that way so that everybody draws them the same way. So the anode is the electrode where oxidation occurs. The cathode is the electrode where reduction occurs. That's always going to be true. One way to memorize it is A and O are vowels, C and R are consonants. Another way to remember it is A comes before C in the alphabet, O comes before R in the alphabet. So anode is where oxidation occurs, cathode is where reduction occurs. That is always, always true. For electrochemical cells, the anode is the negative electrode and the cathode is the positive electrode. That's only for electrochemical cells. Electrolytic cells are the opposite, but notice that there is a little thing here that says don't worry about labeling it as negative and positive on the AP exam. So you don't need to know that for the AP exam. I'm just having it in your notes for when you go to college, but don't worry about it for our test or for the AP exam. So when you look at your battery, you see a positive end and a negative end. The positive end is the cathode, the negative end is the anode. Anode, anion, negative, cathode, cation, positive. So if we said that copper is going to get reduced, then that means that it's going to be your cathode, and zinc is going to get oxidized, so that's going to be your anode. So you put the zinc in the anode and the copper in the cathode. The second thing you need, other than the 2 pieces of metal, are 2 solutions, and you want the solutions to contain these metal ions. So you're going to put your anode and your electrode in solutions, and that solution should contain that metal ion. So for the zinc electrode, you want a solution that contains zinc ions. So you could use any solution. You could use zinc nitrate, zinc chloride, zinc sulfate, anything. Most of the time we use zinc nitrate or nitrate solutions because nitrates are always soluble. They rarely react with anything to form any type of precipitate, so they're not going to interfere with your reaction that's happening, with your redox reaction. So we're going to put the zinc in some zinc nitrate solution. And zinc nitrate solution is basically water with zinc ions and nitrate ions swimming around. We're going to do the same thing for the copper. So we're going to put the copper electrode in a copper solution. Again, we typically use nitrates, but you could always use anything else. And so we're going to use copper 2 nitrate. So you have water with Cu2 pluses and then NO3 minuses swimming around. Okay, so we got our metals, we got our solutions. Next, we need a conducting wire. So we are going to connect our two electrodes, or two pieces of metal, with a wire. And to show that it is a wire and conducting electricity, we put a little circle with a V in it to stand or represent a voltmeter, showing that there is voltage going through. So let's see what is happening here in terms of the reactions. And so let's start with the anode here. So we have zinc reacting, and it's getting oxidized. So let's look at the reaction that's going to happen. We have zinc and zinc 2 plus. And so if I wanted to write an oxidation reaction, which one is going to be your reactant? Which one is going to be your product? Neutral zinc and zinc 2 plus. Which one's the reactant? Well, if you're getting oxidized, that means the charge is going up. So that means we start with the neutral and we go to zinc 2 plus. Right? And then we lose the 2 electrons. Let's look at the reduction reaction. So what's happening is that we have copper and copper 2 plus. So we are reducing, so we're gaining electrons. The charge is getting reduced. So which one is your reactant and which one's your product? Well, if you have neutral copper and copper 2 plus and our charge is getting reduced, it's going down. So that means the Cu2 plus is your reactant and the neutral Cu is your product, and in order for that to happen, you need to gain 2 electrons. So what does that mean? Well, let's start with the anode. So the zinc, that's my reactant, is going to undergo oxidation. It's going to get oxidized, and it's going to produce zinc ions and some electrons. So as time goes by, this electrode, this piece of metal, it's going to get smaller and smaller and smaller because it's going to get used up. And it's going to turn into zinc 2 pluses, which will go into the solutions. So as time goes by, my zinc ion concentration in my solution is going to increase. And it's always going to produce some electrons as well. Where are the electrons going to go? They're going to go through the wire. And so the electrons are going to flow from the anode to the cathode. So again, as time goes by, my piece of zinc electrode here is going to get smaller and smaller and smaller. My zinc ion concentration is going to get higher because the zinc is being oxidized and turning into zinc 2 plus and electrons. Then the electrons are going to flow through the wire from the anode to the cathode. Let's look at what happens here. So I have my Cu2 pluses as my reactants. Well, where's the Cu2 plus coming from? Well, the Cu2 plus is coming from the solution. So the Cu2 plus is going to combine with some electrons. Where are the electrons coming from? Well, the electrons are coming through the wire. So the electrons are coming from the anode to the cathode through the wire. The electrons, when they meet the copper 2 plus, they're going to reduce and they're going to turn into solid copper. And so as time goes by, the concentration of my copper ions in my solution are going to go down and down and down because they're going to get used up. And my copper electrode is going to get bigger and bigger and bigger because neutral copper is being deposited or produced. So when will my reaction stop? Well, my reaction will stop when my reactants run out, right? Which means when my zinc electrode is all used up, remember it's going to get smaller, smaller, smaller. So if I use it all up and I don't have any more solid zinc, then the reaction will stop. That's when your battery's dead. Or when your other reactant runs out, when my copper 2 plus in my solution runs out, then my reaction will stop and my battery will be dead. Now, one thing here is that once one electron is transferred, you see when the zinc is oxidized to go to zinc 2 plus, and then it forms electrons, and the electrons travel through here. Well, guess what? Once an electron travels through here, it builds up a negative charge here. And once the zinc ion goes here, it builds up a positive charge here. And so once one is transferred, that's a problem, because if this becomes negative and this becomes positive, the electrons are never going to flow this way. And so my reaction will stop after one electron is transferred. And so what else do we need? Well, the fourth thing that we need in order for this battery to work, it's not going to work this way. What we need to get it to work is a salt bridge. And so a salt bridge is something that the ions can go through. So sometimes we can use just a piece of filter paper that is soaked in a salt solution. I built a battery before and used a pickle. You can use a potato. You can use a hot dog. You can use all kinds of stuff. Actually, one year I had I did a demo and I used a hot dog as my salt bridge, and then I was absent one day and one of my students actually took a bite of that hot dog. It was disgusting. But anyway, you need some kind of substance here, whether it's a filter paper dipped in salt solution or a hot dog or a cucumber or whatever it is, something that allows flow of ions. And usually when we do this in the lab, like I said, we get a piece of filter paper that we dip in a salt solution. You want to pick a salt solution that won't interfere with any of the reactions. And so usually we dip the filter paper in potassium nitrate. So not always, but usually this is filter paper dipped in KNO3 solution. And so what's going to happen here is that inside of this is your salt bridge. So inside of your salt bridge, your nitrates are going to flow this way, and your K pluses are going to flow this way. Why? To neutralize the charge. So, because as you form zinc 2 pluses here, you need something negative to neutralize it. And as you transfer electrons here, you need something positive to neutralize it. And so whatever you used as your salt that you dipped your filter paper or whatever your salt bridge is, whatever ions it contains, the positive ion is going to transfer towards the cathode, the negative ion is going to transfer towards the anode. That way it neutralizes the charge and the electrons are able to flow. And the electrons will flow from the negative to the positive, from the anode to the cathode. If you look at your reduction potentials here, you will see that the reduction potential for copper is 0.34 volts. Remember, we said this is measured in volts. This is going to tell us the difference in reduction potential will tell us the voltage of our battery. So I'm going to write this down, that it's 0.34 volts for the reduction of copper. So I'm going to go back to here, and I'm going to write that the reduction potential here is 0.34 volts. Now let's look at the potential for the zinc. Well, this is not a reduction equation, right? This is an oxidation equation. So if you look at the table of reduction potentials, you will find zinc, but this is the reduction equation, and this is the reduction potential. So if I'm oxidizing my zinc, I need to flip this reaction. If you flip this reaction, you'll get the reaction that we have. You'll get zinc yields zinc 2 plus 2 electrons. That's the reaction that we have, which is the oxidation. And so if you flip the reaction, you flip the potential. And so the oxidation potential for zinc would be plus 0.76. So whatever is being reduced, you're going to write down the potential as is. Whatever is being oxidized, you flip the equation and you flip the potential as well. So instead of negative 0.76, we're going to flip that to make it positive 0.76. So the potential for this one is plus 0.76 volts. So then if I want the potential for my battery, I write cell potential, that's for the electrochemical cell, the potential, is going to be the sum of both of these, so 0.76 volts plus 0.34 volts. It's going to be 1.10 volts. And so that's the voltage for this battery that I have built. So when you're writing your equations and your potential, for the reduction one, you can just copy the equation and copy the potential as is from your table. If you look at your table, this equation is the equation that we have, and this potential is what we have. For the oxidation one, for the anode, you're going to flip it. So you're going to flip the equation, and you're going to flip the potential as well. And then to figure out the potential for the whole battery, you just add them up. If you wanted the overall equation for what's happening in this battery, you add these two reactions together. And so I'm going to add my reactants together, then I'll put an arrow and put my products. And so I'd get zinc plus 2 electrons plus Cu2 plus yields Zn2 plus 2 electrons plus copper. Remember when we used to balance redox reactions? If you did it correctly, your electrons should cancel. And so your overall reaction is zinc plus Cu2 plus yields Zn2 plus Cu. That's the overall equation. And 1.10 volts is the overall cell potential or voltage of your battery. Again, this battery would die, it wouldn't work anymore once you run out of your solid zinc or once you run out of your copper 2+ that's in your solution right here.